Hi, this is Utkarsh Ahuja from EC3. I've been doing winter training on the topic Discrete Time Systems Part 1, that is a time domain analysis on edX. So my tutor was Richard G. Baronick. He's from the Rice University and he's from the EECS department. So let's get further. The course which I completed up till today is this. I actually had completed all 4 weeks. Well, it was 5 weeks. Fifth week was for the review and test series or something like that. I completed the complete course. Up to properties of convolution. Okay. We were asked to complete up till week 2, but I completed the complete course. So, anyways, let's get further. During the 2 weeks, I understood types of fundamental signals, vector description of signals. These are the two main branches which I'll be concluding in this presentation. What is a signal? Well, in the starting, if you start with the presentation, what is a signal? A signal is a very detectable physical quantity which by means or information can be transmitted. This is the statement by Merriam-Webster. And they carry information. Examples: speech signals transmit language via acoustic waves. Radar signals transmit the position and velocity of targets via electromagnetic waves. Electrophysiology signals transmit information about processes inside the body. Financial signals transmit information about events in the economy. Signal processing systems manipulate the information carried by signals. This is a course about signals and systems. So that's what we started in the beginning. So what did I learn in the first week one is this: periodization via modular arithmetic. So as you can see that if a signal is repetitive, if a signal is let's say periodic, then we can have the same values after some period of time. So we represent it as in a circular format, as you can see below, and then after time phases it repeats and repeats and it goes on repeating itself after its own period. So that's modular arithmetic. So in MATLAB we have many signals to implement with. So I played with these key test signals usually, that is the delta function, the unit step function, unit pulse, real exponential, and sinusoid and complex exponential. So sinusoid is a simple it's a simple sine wave, and they are the basic form of signals which every signal processor or signal processing software uses. Either it may be your laptop, either maybe anything in the world, in the physical world, which is concluded with electronics and software. It uses all sorts of sinusoids, and it uses Fourier analyses, or the DFT or the DTFT. Okay, we will introduce real value sinusoids, complex sinusoid, and complex exponentials. So this is a simple sinusoid which I learned about. Complex sinusoid, which I also learned about. So we can have two signals. Let's say e to the j omega phi is equal to 1. Let's say this is equal to 1. So cos omega, we can have the Euler's form. Euler is an entity. I can split this equation on the right and on the left side into right side as cos omega n plus phi plus j times sine omega n plus phi. So these are my two signals. You can see up and down. When I add these two signals up, I should get this signal on the left side via Euler's identity. This is a complex sinusoid, and the complex sinusoid is a helix. The right side is the example or the screenshot taken by me from the website or from the where I was learning, and this is this on the left side is a small video. You can see it here. So I'm showing here, although the x-axis is not visible because there's less space and recording space also, but I'm showing here this is the y-axis perpendicular, z-axis, and the left one is the x-axis, or the last one is the x-axis. So when we add these two signals, again I'll play this video, when we add the below signal to the perpendicular y signal, we get a z signal, and this is a complex sinusoid, and it's a helix. So let's just imagine, let's say if my amplitude each time adds up to the amplitude before, so this signal goes on to increase above and above, and it will enlarge the size of a helix. And so as the enlargement of the size of a helix, the complete rotation time will decrease, and so the period will decrease. So that's what we learned in this part of the presentation, that when we increase the amplitude of the signal, then the time taken by it to complete a rotation, or let's say revolution, will be much higher than the before one. And that's pretty how that's intuitive, and we can think that like that ways. So this is a vector description of signal, which I also learned, and it's a table of contents which talks about lecture in three parts: vector spaces, linear combination, plus the MATLAB demo, which I'll also show it here. Strength of a vector. Linear combination is this simple combination, as the addition or subtraction in a matrix format. So I've just shown a screenshot here. This is a MATLAB work which I did in accordance to it. I'll play it here. As you can see, I took two matrices and I add those them down. This is x plus y equals z. That's how we ended here in this presentation, the small part of this video.
Hi,
this is another this is another video I made
again.
I introduced
and I'll be discussing
myself
about
again
now
in this video.
what sort of
I'll play it here.
things or what sort of projects or what sort of, let's say, signals I've been studying on the MATLAB with the help of this course. The tutor on this course told me about few of the sounds which I'll be computing right now on the MATLAB. That's my MATLAB. Okay, that's the code, the sketch code which I had already made before this presentation or before recording this. So you can see that there are three variables up there. Okay, and then there is a sine wave, then there is a chirp, that is also signal, sound signal, and that's a white Gaussian noise signal, right? So let's just run this code because I need my three variables. I have these three variables in the workspace. You can see that. Now first I'll be running the sine wave. This is simple sine wave. And that's a figure of the sine wave. You can see here. That's a figure of the sine wave. I also plotted it. So I'll dock it into the window. Okay, here, right? The next is the chirp. This is the chirp command, the chirp signal, and I'll be copying it here, and you can listen to it. So this is a signal which is used in sonar, in the geophysics, and getting into the known to what is beneath the earth, and these signals are used again and again so that we can get an idea how much far the object is, what sort of object is available beneath the earth, or let's say a long distance away. What are we seeking into? Into the metals or into the rocks or whatsoever. So this signal helps us in noting those things down, and it tells about its frequencies and the reflection which comes in from the it gets us reflected signals, and then we conclude that what is going on inside that material or what sort of material that is. And that's the white Gaussian noise in the next signals I'll be plotting in. Okay, so that's a Gaussian noise. That's a signal when you get when you tune into between different radio stations, or let's say in let's say 5 to 6 years before this time. Presently we don't have that cable TVs. We now have LED UHD TVs and LED TVs, and we have set-top boxes. But at that time we used to have this white noise, and that has to have a this sound which I had already played above. So let's play it again. So that's how I learned many things here. This is one of those parts in the presentation. Rest I'll be showing it later. Thank you very much.
Okay, After listening to this, let's get to the next slide. Okay, now the end topic after 2 weeks is Cauchy-Schwarz inequality, which I actually learned in the last. I compare these signals. Let's say I have a transmitter and I have a receiver, and there is a very noisy channel between. I send one signal from the transmitter after source coding, let's say compression or the Huffman coding and the syndrome coding and many more, or encryption. The noisy channel will distort my input signal. And after receiving that signal, now I have to conclude what is zero, which bit is 0 and which bit is 1. So Cauchy-Schwarz inequality helps me in this process. So let's say if I have a standard, I'm saying I'm a receiver, I'll be using the NRZ coding, and I'm saying to the receiver, you also use the NRZ coding. So we both know what is R0 and what is R1. Bit 0 is how it is represented, and bit 1 how is it represented. So we both know the standards. We are following that standard, and in accordance to that standard, we'll be concluding that what sort of bit has been received. Okay. So this is a two norm I've calculated, which is cos theta xy, which is real part of xy upon double mod x double mod 2 double mod y double mod 2. And it quantifies the comparison, a powerful and ubiquitous signal processing tool. Note that development will emphasize intuition over rigor, and that's in the future presentation which we'll be learning into. Okay, and so so this is the part of the video. So now we're going to learn about what is a two norm or what is orthogonality between two signals. Why do we study this? Because let's say if I have a transmitter and I'm sending a signal, okay, and I receive a signal, which then I have to conclude that the bit, which sort of bit was sent. For example, I'll show it here. Let's say if I have sent a 0 signal, you can see here. Okay, let this be a 0 signal. Let this be a 0 signal. Okay, I represent this as 0. Now with the same principle, now I actually I'm gonna send one signal. Let this be one signal, and then I'm gonna rub this part. And so my line goes here and goes straight over there. Let's say this is 1. This is 1. I represent this as 1. Okay. So now what we do is in a product, let's say if I have a signal very distorted sort of, let's say I'll use a brush, simple brush. Let's say this was my axis, the axis, and that's my signal, some sort of a very distorted form, right? So what do we do in two norm? What do we do in two norm? What we do is let's say if I have a signal which comes in this form, and I also receive a signal in a perfect sense. Let's say my system is in ideal form, so I also receive the same signal. Let's say I'll make a copy of this. If I have sent this signal, then I'll receive the signals. So when I multiply both of them, so let's say if I multiply each part by each part, if each small dx by dx of one signal, of this signal to that signal, then in the end I should get 1 after multiplication. Why is that? Because we conclude to the point that when the two signals are out of phase, we multiply them, then they add up to 0. Let's say if I multiply this 0 and then this 1, I'll get one cycle up and one cycle down. And when I add the complete signal to the complete signal to get a complete absolute value, then I get a 0. As we can see here in the presentation also, I've taken this real xy upon xy plus this one. So what we are doing is we are actually taking a complete signal and then we are taking it to norm. We are adding the complete signal after multiplying. So what we get is either 1 or 0. So in this case, if I multiply 0, this signal with this signal, I again get this signal again, the 1 part. So when I add this cycle, let's say I'll highlight that part. If I add this part, if I add this part to this part, I will get a 0. But that's the same thing when we multiply two signals after receiving them from the communicator. Okay, in MATLAB we can do compression coding also. We can when we go in a signal processing, we actually compress a code. We can actually go for syndrome coding, and we can use this method. MATLAB is able to do all three of those and many more. So in MATLAB what we did is this. Okay, first let me clear it, then I'll show the code. Okay, okay. So this is my code here. I'll show it. So I've taken 3 variables, n and x0 and 4 variables. Let's say x0 and x1 are the signals I've been transferring. Okay, so in subplot I'll stem these signals. As you can see, mark a line width, and signal x1 transmit to send signal digital 0. This is digital 0, and the next one is and the above one is signal transmit send a digital 0, and this is digital 1. Okay, I made a mistake. Okay, this was signal 1. Sorry, this is digital 1. Fine. Okay. Now when I run this code, complete code, I get this. Okay. I get this code, right? These are my two signals. The signal x0 transmitted to sender digital 0, signal x1 transmitted to sender digital 1. You can see that's the same example I've tried to make in the paint here, right? So I go back to my figures and explain from here. Now when I receive a signal, let's say I'll take a random signal which I had received here, and this is the random signal. You can see RANDN. Now what's the difference between RAND command and RANDN is that RAND differentiates values between 0 to 1 only. If I use a let's say if I try to make a matrix, let's say 3, 2, 3 rows and 2 columns, and use a rand function, then it will distribute all 6 values between 0 and 1. So all values will be less than 1 and greater than 0. But in this case, when we use rand n, we are actually taking numbers. We are taking natural numbers, or the whole number, natural numbers only, and then we actually are plotting the signal. It's a random signal, and here you can see this is random signal multiplied by 0.2, a small value, and it is added to x0. You can see here x0. X0, I'm trying to take a signal which is my which is the transmitted digital 0 signal, and then I'll show and compare what I actually did in this MATLAB. Okay, so I'll pick this signal and I'll copy it here. Okay, I'll copy it here and let's run it. So I get my 3 signals. Yeah, this is my receive signal. Was it a 0 or 1? Now I have to check this. Now what I do is I actually take an inner product between those two. So this is the command of this inner product. I'm taking the inner product of those two, and then let's calculate what it actually gives me. So if I Control C and I copy it here, enter. So inner product 0 is 0.08043 and inner product 1 is 0.25x63. So it shows me that the values of inner product of getting a 0 is much closer to 1 rather than the inner product 1, which is very less than 1, which is very closer to 0. So it shows me that signal which I received was a digital 0 rather than digital 1. In other case, now if I change the things here, if not x0, I change this as x1 and I implement it here on the left side. Okay, I'll implement this as x1 now. Again, I'll run this code and now let's see what happens. Okay, control C. Now I implement this signal. Now what do we get? We get again that was it a 0 or 1? Now I take an inner product between these two. Now let's see what happens. So now you can see the inner product 1 is 9.9794 and inner product 0 is 0.1643. So it shows me that it is quite near to 1 in the case of when digital 1 was sent rather than digital 0. So this signal here is now a digital 1, not a digital 0. So in this case we can conclude to the fact that what sort of signal which was sent, even after compression, even after syndrome coding, even after any sort of source coding, the channel will distort the input signal, the going output signal, or the, let's say, receiving signal. So somehow we have to run these codes to get a signal which to confirm it, whether it's a 0 or whether it's a 1. So in those cases these codes are helpful, and that's the reason why we learn this methods, or the Cauchy-Schwarz inequality, or let's say the 2 norm or the P norm. P norm is very higher thing after this, although I cannot conclude those topics because these topics were more than enough to conclude to the statements, because after these two topics we had a week 3, but as asked in week we were up till week 2, so I concluded here and I'll end this presentation over here only. Thank you very much for listening to me.